What lies behind the breakthroughs in AI? This module unveils the method behind neural networks, understand their strengths, limits, and how they learn. An artificial neuron processes several inputs, each with a weight indicating its importance. These inputs are summed and passed through a function to generate an output. The neuron's power is minimal on its own. However, connecting many neurons and learning the right weights is where the magic happens. This is the foundation of neural network functionality. Inputs are signals from other neurons or features. Each input is multiplied by a weight. The weighted inputs are summed into a total. An activation function then converts this total into the neuron's output. The network learns by adjusting these weights to improve its predictions. Neurons stack into layers to form networks. The input layer receives raw data. Hidden layers process this data into complex patterns. The output layer provides the final result. Signals flow through these layers. Learning from weighted connections. Hidden layers build complex patterns from simple ones. Early layers might detect basic features like edges. Middle layers combine these into shapes. Later layers recognize objects like faces. This layered approach is key to solving tasks effectively. Training involves predicting, checking errors, and adjusting weights. Initially, weights are random, leading to poor guesses. Examples are shown, and errors are measured. Weights are adjusted to improve predictions. Repeating this process across numerous examples refines the network. The forward pass involves feeding an example into the network. Signals move through layers to produce a prediction. The prediction is compared to the correct answer. Loss measures the prediction's error. Minimizing this loss is the goal of training. Backpropagation determines each weight's contribution to the error. It assigns responsibility for the error to each weight. Weights are adjusted based on their impact. This efficient method improves millions of weights simultaneously. It is crucial for training large networks. Gradient descent visualizes error as a landscape. Training involves moving downhill to minimize error. Steps are taken in the direction of decreasing error. Proper step size is crucial to avoid overshooting. This method tunes the network effectively. Deep learning involves networks with many hidden layers. Depth allows learning of complex layered patterns. Shallow networks have limited feature combination. Deep networks build abstract representations. This depth is essential for modern AI success. Deep learning revolutionized vision, speech, and language. It enables object recognition in images, converts speech to text accurately, translates and summarizes text fluently, generates new content from prompts effectively. Image networks scan patches across pictures. They detect patterns regardless of position. This efficiency makes them ideal for vision tasks. Sharing detectors across images improves performance. They are the backbone of computer vision. Language networks handle sequences and context. They weigh word relationships across sentences. Attention-based designs track meaning over distance. This innovation enabled large language models. Older methods struggled with context retention. This ability allows them to answer questions. However, they predict plausible text, not verified truth. They should be checked, not blindly trusted. Neural networks excel at finding subtle patterns. They improve with more data and computing power. Automatically learn useful features, can transfer knowledge to related tasks. They are often the strongest tool for rich pattern data. Neural networks require large data amounts. they can be confidently wrong without doubt, vulnerable to small, deliberate input changes. Power and fragility coexist in these systems. Their failures can be as dramatic as their successes. Deep networks' decisions are hard to explain. Millions of weights obscure reasoning. Tools estimate important inputs but are approximations. Opacity is problematic in critical decisions. Simpler models are sometimes preferred for transparency. Training requires large datasets and computing power. Specialist hardware and skilled people are needed. Bigger isn't always better. Smaller models may suffice. Training has energy and environmental costs. Most adapt existing models rather than start from scratch. Neural networks power daily tools like assistants. They support diagnostics in health and industry. Language models aid in drafting and summarizing. They enhance accessibility with captions and translations. These networks are integral to modern technology. Consider what a single neuron does. Reflect on hidden layers' contributions. Understand why language models can be confidently wrong. Evaluate the black box problem's impact on your work. These reflections are crucial for mastering neural networks. Artificial neurons weigh inputs and fire outputs. Layers build complex patterns, enabling deep networks. Training involves forward pass, error measurement, and backpropagation. Deep learning powers vision, speech, and language tasks. Neural networks are powerful yet fragile, requiring careful handling. Neural networks transform simple parts into learning systems. They reveal rich patterns with both power and fragility. Understanding their mechanics is key to harnessing their potential.